Okay. So maybe at this stage here we could actually see what happens. Um, so if we do that, what do we have to do? We have to go to the actually the same code we were looking at in the K-means lesson group, and we now set parallelism equal to 2. Remember, we set these basic parameters: max, mean, parallelism, number of iterations, and threshold. We'll keep max mean to be 1, and to make it more interesting, number of iterations to be 1. But we'll set parallelism equal to 2. Then we do select all and copy, and then we put this into our IPython window, and I forgot to do the copy. And it's now running away with the parallelism equal to 2. And if everything's right, it should give you similar answers to the parallelism equal to 1 case. Here they pop. Remember, we have 8 windows. We'll just look at those windows to see they don't look silly. So what is this top window? That's the case of what is it? Very large clusters, clustered into 4. It looks a perfect job has been done. It's got the right answer. So that one is fine. What do we have here? Remember, we're running with iterations equal to 1, so there is some greater probability than you would normally have if you ran with iterations of 20 to get a distorted answer. And here we're running with very large clusters and clustered into 2, and this looks pretty sensible. The top 2 slightly bigger initial clusters are joined together, and the found cluster and the bottom 2 are joined together. That's again probably the natural answer. So this parallelism equals 2 is suddenly giving reasonable answers here. Now we have the 4 small clusters and clustered into 4, and the answer is exactly reasonable. Each of the found clusters is equal to one of the original clusters, which are now completely separate. Remember, we had an interesting discussion of the what happens when you take the 4 small clusters and cluster them into 2. You've got these 2 solutions: either the natural one, which you would have guessed to be best, which was pairs, but I showed actually the 1 and 3 was in fact in some limit of 0 size original clusters, actually the optimal. And you can see it found the 1 and 3 case here. This cluster here is found as a single cluster, and these 3 are joined together with this center as the other cluster. Let's see, on this one, here we have 8 clusters. We have the top 2, each divided into 2, and the bottom 1 divided into 3, and 1 divided into 1. This is the so-called large clusters, not the very large, just large. And this is not obviously the best, but it's not an unreasonable solution. There's no, it looks okay. Now we have 6 clusters in the case of the large radius case. And this is certainly pretty reasonable. Each of the bottom clusters is found exactly correct. Each of the top clusters is divided into 2. That's probably the solution we think is most plausible. And here we have the, what is this one? This is the large case clustered into 4, and it's sort of perfect. Each of the original clusters is found by by K-means. And we have one more to go. Let's see how this looks. These are large clusters, original generated large clusters clustered into two, and now we've got these two joined together and these two joined together. And of course, whether it chooses these two or these two is certainly not obvious which is best, and this is at least a reasonable solution. All right, so we found parallelism equals 2, got reasonable answers, and that's all built into exactly the same code we were using in the original K-means technology lecture. All right, let's return to the all right, now we're returning to the PowerPoint. And in fact, we've reached the last slide. So let's just go to this as the last slide. And what we just did is trivial to divide, to do it for p-way parallelism for any value of p. You divide the data into p parts. The results we showed in the MapReduce lesson group actually went up to quite a lot of cores, 256, so 250, divided into 256 parts. Now you have to run each of those parts separately, with each part having 1/pth of the data. So if it's just parallelism of 2, each has half the data, but they have all the centers, because centers have contributions from each of the data. And then you need to do, as we saw in the reduction already, you sum the contributions to the centers from each process, and you sum the contribution to distortion conversion criterion, or you actually max it if you for the max version of the convergence criteria. The maps can run in parallel. Reduce, you can decide to run either sequentially, or if you have large levels of the parallelism, you use some parallelism there. And we've already stressed many times the difference between the sequential code and the MapReduce code, just a very simple movement of the division by the total number of points out of the initial calculation and put it right at the end. So thank you very much. That's the end of our discussion of MapReduce applied to K-means in Python. Thank you very much. This is Geoffrey Fox signing out.